Hello, friends, and welcome to the second lesson in our Unit 3 equilibrium. So we're going to be talking about the reaction quotient, Q, as well as Le Chatelier's principle. So the reaction quotient, which is given the variable Q, measures the relative amounts of product and reactant present during a reaction at any point in time. That is the key difference here between the reaction quotient and the equilibrium constant. Q is at any point in time. But if you notice, other than that, Q looks exactly like K, and that's because it is exactly like K. So if you remember, so K is concentrations raised to their coefficient of products over reactants. So there is literally no way in which Q is different from K, except that Q is at any point in time, while K is only at equilibrium. So when we calculate Q, we plug in any concentration or pressure. But when we calculate K, we have to plug in concentrations or pressure at equilibrium. That's the difference, okay? So what's the point in Q? Well, we use Q to determine which way our reaction needs to proceed, left or right, in order to reach equilibrium. So Q kind of tells us how far away from equilibrium are we. Okay, so we're going to start with this example. Up here, I have the equation 2 sulfur dioxides plus oxygen is in equilibrium with 2 sulfur trioxides. So sulfur dioxide and oxygen are my reactants, and sulfur trioxide is my product, okay? So we have two scenarios here. So we did this in class in our simulation and talked about how we can start with all reactants, all products, or a mixture of both. So here, I'm going to go through the two scenarios of starting with reactants only and starting with products only. So if I start with reactants only, then my concentration of reactants is going to start higher and then decrease over time until it steadies out at equilibrium. And then my product is going to start low and increase over time until it gets to equilibrium, where it levels out. If I start, if I start with reactants only, well, Q, just products over reactants always, okay? So if I don't have any product, then I have 0 over reactants, and so Q starts at 0. But as I build product, Q is going to increase until it reaches the value of K. All right, so if I start with all products, Q is going to increase until it gets the value of K. If I start with all reactants, sorry, I just misspoke. Now, if I start with all products, then my concentration of product is going to start high and it's going to decrease until it levels off. Then my reactants are going to start at 0 and then it's going to increase until they level off. But now let's think about Q. Again, Q is products over reactants. If I start with products only, I have some amount of product over 0, which essentially is like infinity. It's undefinable. It's going to be some really huge undefinable number, okay? But what I do know then is as the reaction proceeds, Q is going to decrease until it reaches the value of K. So what we're getting at then is that at equilibrium, Q equals K. In this scenario, Q had to increase in order to get towards K. And in this scenario, Q had to decrease in order to get towards K. So I mentioned that sometimes we like to refer to, or the video did also, nirvana. So we're going to say that equilibrium is nirvana. And we're trying to get towards nirvana. So at nirvana, or at equilibrium, we have some value of K. So let's say that we start with some initial concentrations or initial pressures where Q is less than K. Q is some value less than K. Then Q is going to have to increase in order to get to where Q equals K. So Q is going to have to increase in order to get to nirvana. So let's say that I start with Q greater than K. I start with some value that Q is larger than K. Then Q has to decrease in order to get toward nirvana, where Q equals K. So Q is going to increase. Here, Q is going to decrease. Well, remember, Q is products over reactants. So in order for Q to increase, we need to increase products and decrease reactants. So we shift right. In order for Q to decrease, then I need my reactants to increase and my products to decrease, so I've got to shift left. So hopefully this kind of image will help you to remember, if Q is less than K, I got to shift right to make Q bigger. If Q is greater than K, I have to shift left to make Q smaller. So this is just another slide that summarizes that. So if Q is less than K, I have to shift right in order to reach equilibrium. If Q is greater than K, I have to shift left in order to reach equilibrium. If Q equals K, then I am at equilibrium. So let's look at this example. I am given this equilibrium, and I'm told that the K value is 4.72. So I have a superproduct favored equilibrium position. So if the concentration of nitrogen dioxide equals 0.4 and dinitrogen tetroxide equals 0.1, is the reaction mixture at equilibrium? If not, predict which reaction it will proceed to get to equilibrium. So the only way for this to be at equilibrium is for Q to equal K. So we're looking at, does Q equal K? Well, when I plug in the concentrations that I was given, product over reactant, raise their coefficient, so 0.1 over 0.4 squared equals 0.625. Q does not equal K, so I am not at equilibrium. So what I'm going to do now is I'm going to compare Q to K. Well, if I compare 0.625 to 4.72, Q is less than K. So if Q is less than K, I have to shift right. I've got to make more product in order to increase the value of Q for it to move towards a value of 4.72. So let's do a few more practice problems. So if you would like, you could pause the video, do these on your own, and then resume. Okay, so we're given the either initial concentrations or the partial pressures, and then we're given the K value, so the equilibrium constant. So we're asked to determine which way the reaction needs to proceed in order to get towards equilibrium. So for A, the first thing I'm going to do is I'm going to write my expression. And I'm going to write Q because we're calculating Q. All right, I always recommend that you write just the expression first, because sometimes if you just start plugging numbers in without writing the expression first, sometimes you forget your superscripts. You forget to raise it to the coefficient. All right, so now that I've written my expression, I'm going to plug in these concentrations that I'm given. So 0.12, 0.15, whoops, the 0.12 is cubed. See, I even wrote it and almost forgot. And then 0.5 squared. All right, so now I'm going to plug this into my calculator. 0.12 cubed times 0.15 divided by 0.5 squared. And I got 0.001. Well, my K value is 17. So for A, Q is definitely less, much less than K. So Q needs to increase in order to equal K. So we have to shift right. Right? So now for B, this time we're using pressures, but we don't write it any differently, minus the fact that we just use the P to represent pressure. Sorry, I'm running out of room. All right, I'm going to plug in my numbers. My initial pressure of, oh no, oh, that was down there. I was like, it got cut off. H2 is 10. So 10 cubed times 10 over 2 squared. And plug that into my calculator. I get 2,500. Well, K is 6.8 times 10 to the 4th. So Q again is less than K, so I have to shift right. All right, I'm going to do C up here since I'm out of room. All right, so I'm going to write my expression for Q. Concentration of SO2 squared O2 divided by SO3 squared. I'm going to plug my values that I'm given into my equation. They're all equal to 2. So 2 squared times 2 divided by 2 squared equals 2. So it tells me that K is 0.23. So this time Q is greater than K, so we are going to shift left. Because if Q is greater than K, we have got to decrease in order for Q to equal K at equilibrium, so we got to shift to the left. Okay, so that was the reaction quotient. We used the reaction quotient to predict which way a reaction has to shift to get to equilibrium. Now we're moving on to something called Le Chatelier's principle, which is how a system at equilibrium responds when some kind of stressor is added. So Le Chatelier's principle says if a change is imposed on a system at equilibrium, it's important that we note that at equilibrium, the position of the equilibrium will shift in a direction that reduces whatever change that was and restores equilibrium. So let's say like if we were in balance right here, so we're in equilibrium, something happens, we're going to talk about what those some things are. Something happens and it gets us off balance. Well, we got to counteract that to get us back in balance or get us back to equilibrium. So if something happens, we're going to shift back. Something happens, we're going to shift back. So when this stressor, whatever stressor it is is added, Q doesn't equal K anymore because I've changed it. And so the system has to shift to restore Q equal to K. And so the stressors that we're going to look at are what happens if we change concentration once equilibrium has been established, what happens to gaseous equilibrium if we change the pressure, and then what happens to equilibrium once we change temperature. So the first is a change in concentration. So the first thing we're going to talk about is, let's say we add reactants or products. The system is going to have to shift to use up that addition. So if I add reactant, well, I need to use up those reactants. So then I'm going to shift right. So if I add reactants, I'm going to shift right to use up those added reactants, and that's going to produce more product, and then I'm going to be back at equilibrium. Now, what if I add product? Well, I need to use up that added product, so I have to shift left in order to use up that added product. So then I make more reactant, and then my Q is going to equal K again. I'm going to be back at equilibrium. So if I add reactants, I shift right. If I add products, I shift left. What if we take some away? So what if I remove product? So I make product go down. Well, then I need to make more of it. So I'm going to have to shift right to replace it. So if I remove my product, I'm going to shift to the right. What happens if I remove some reactant? Well, then I need to make more of it to replace it. So I'm going to shift, forgot my color coding. I'm going to shift left. So if I take out reactant, I got to shift right to replace it. If I take out product, I got to shift left to replace it. Easy enough. So let's look at these examples. So we have this reaction, P4 plus 6 chlorines makes 4 phosphorus trichlorides. Predict which way the equilibrium will shift for each of the following changes. So basically what you need to determine, is it a reactant or is it a product? And then are we adding or taking it away? So Cl2 is a reactant. So if I add reactant, I need to use it up. So I'm going to shift to the right. That's going to use up the added chlorine. If I remove some of that chlorine, which again is a reactant, if I take away a reactant, I need to remake it or replace it, so I got to shift left to make more of that chlorine. Now, the second two are a little bit tricky, because if we look at this reaction, I have a solid and I have a liquid in there. So if I wrote K for this reaction, I would actually just have 1 over chlorine to the 6, because solids and liquids don't appear in an equilibrium expression. So if the change is to a substance not in expression, in the equilibrium expression, then there's going to be no change. If it's not part of the equilibrium expression, changing it is not going to change the position of the equilibrium. So if I take out P4, it's not going to matter because it's a solid, so it's going to be no change. And if I add PCl3, no change because it's a liquid and those are not in the equilibrium expression. So only changes to aqueous and gaseous reactants and products are going to shift equilibrium, forcing us to shift right or left to restore it. Our second change we can make is a change in pressure. Now it's important to note that, like we talked about with Kp, we only write it for gaseous equations. So pressure is only going to affect systems where gases are involved. and it's only going to affect systems where the total number of gas molecules changes. And I will show you why that's the case in just a moment. But first, we need to do a little review of concentration, pressure, and volume, because I can't just directly change the pressure most of the time. I've got to do something else that indirectly changes the pressure. So there are a couple of things I can do in order to change the pressure. I can change the volume of the container. So here, I'm actually going to rewrite this down here. So to change pressure, I can change the volume of the container, or I can change the concentrations of substances. So if I change the volume of the container, what does volume do to pressure? Remember, they are inversely proportional. So if I increase the volume, I decrease the pressure, and vice versa. But now concentration and pressure are directly proportional. So if I increase the concentration, that is in turn increasing the pressure. So why do I tell you all of this before I tell you how we shift to counteract that change? Because a question is most likely not going to ask you what happens if you increase the pressure. It's going to ask you what happens if you decrease the volume of the container. And you need to know then that decreasing the volume of the container increases the pressure. So what happens then? If we increase the pressure by increasing the concentration or by decreasing the volume, either of those two changes are going to increase my pressure. I have to shift to the side with fewer gas molecules. Because if I've upped the pressure, shifting to the side with fewer gas molecules is going to decrease my pressure. Now, if I increase the pressure by adding an inert gas, which just means it doesn't react, there's going to be no effect. Because there's no way, if it's not part of the reaction, there's no way to alter its change. And so if it's an inert gas, it's not part of the actual reaction. You can think of it like it's not part of the equilibrium expression. So no change is going to occur. Now, if I decrease the pressure, which I can do by decreasing the concentration or by increasing the volume, then I have to shift to the side with more gas molecules. Because if I decrease my pressure, I got to shift to more gas molecules so that I increase my pressure back up. Because the more gas molecules there are moving around and colliding with each other in the container, the more pressure there is. So let's look at these examples. So I'm given this reaction, N2O4 in equilibrium with 2 nitrogen dioxides, and I'm going to predict the shift. If I increase the volume of the container, what does that do to my pressure? Increasing the volume is going to decrease pressure. So if I decrease pressure, I need to shift to the side with more gas molecules. Well, there's only one gas molecule in the reactant, but there are 2 gas molecules in the product. So that means I'm going to shift to the right. If I decrease the volume of the container, I'm going to increase the pressure. Think about squishing a balloon. It's going to eventually explode. Then I got to shift to the side with less gas molecules, which for this one is to the left. Now for this bottom reaction, increasing the volume, again, decreases the pressure. Decreasing the volume increases the pressure. But if I look up here, I have 2 gas molecules in the reactants and I have 2 gas molecules in the products. So I don't have a side with less gas molecules. So these are both going to be no change. So when we're looking at pressure, we need to first figure out, does pressure go up or down? Because remember, we're going to be told indirect changes, like changing the volume or changing the concentration. Then you're going to determine the shift. All right. So my third and final stressor is changing the temperature. Okay. Changing temperature does change the value of K, but Le Chatelier's principle still applies just the same. Now, changing pressure depended on where there was more gas molecules in the reactants or product. Changing temperature depends on if the reaction is endothermic or exothermic. So if we remember, an endothermic reaction means it is gaining energy, so delta H is positive. The way we know it's an exothermic reaction, it loses heat, so delta H is negative. So for an exothermic reaction, we just think of endothermic reaction, we think of heat as a reactant. And for an exothermic reaction, we simply treat heat as a product. All right. So now that we know for an endothermic reaction, heat is a reactant, and for an exothermic reaction, heat is a product, we think of it the same way we thought of when we added or removed reactants and products. So for an exothermic reaction, meaning negative delta H, so heat is a product. If I increase the temperature, that's like adding energy, so that's like adding a product, so I shift left. If I decrease the temperature, that's like removing energy, which is like removing a product, so I shift to the right. For an endothermic reaction, that means we have a positive delta H, so then that's treating heat as a reactant. So if I increase the temperature, that's adding energy, which is adding a reactant, so then I shift to the right. If I decrease temperature, that's taking away energy, which is taking away a reactant, so I shift to the left. So adding a reactant, shifting right, removing a reactant, shifting left, that's the same as when we talked about concentration. It's just this time, the thing we're adding and removing is heat, and so it depends on being endo or exothermic. So looking at this example, I'm given this equation and the delta H value. The delta H value is negative, so right off the bat, that tells me that this is exothermic. So negative delta H means it's exothermic, so heat is a product. So if I increase the temperature, that's like adding a product. And when I add a product, I have to shift left. If I decrease the temperature, that's like removing a product. When I remove a product, I have to shift right. Okay, so this chart summarizes all those changes we just talked about. So changing concentration, changing temperature, and then changing volume, which is indirectly changing pressure. All right, so this summarizes all of that. Concentration, if we increase, we shift to consume it. If we decrease, we shift to replace it. Temperature, if we increase, we shift to consume that added energy. If we decrease, we shift to replace it. Volume, if we increase the volume, that decreases the pressure, so you shift to where there's more gas. If we decrease the volume, we increase the pressure, so we shift to where there's less gas. If we add a catalyst, that could be something. That's not going to affect the equilibrium position. It's going to get you to the products faster, doesn't change your position of equilibrium. The other example of no change is an inert gas. that's going to have no effect because it's not part of the reaction. Something else that we could put right here is variables or things that don't affect the chemical equilibria. We could say changing a solid or liquid, because those don't appear in the equilibrium expression. Or we could say changing pressure of reaction with the same number of gas molecules on both sides. So remember how we said if there's 2 in the reactants, 2 in the products, there's no way to shift to a side with fewer or less gas molecules, so that's no change. So here are kind of 4 scenarios where you could have no change. All right, so let's do some practice. I would pause, do it yourself, and then resume. So how will the increase in temperature affect each of the following, and then how will a decrease in volume? So I'm just going to do 2 columns. I'm going to do increase in temperature, and I'll write how that's going to change it, and then a decrease in volume, which in turn is an increase in pressure. So let's start with an increase in temperature. For this first reaction, it's endothermic. So heat is a reactant. So if I increase temperature, that's like adding a reactant. So I have to shift to the right. Same for the second one. It's endothermic. So heat is a reactant. So if I increase the temp, I shift to the right. Down here, these are both exothermic. So heat is a product. So if heat's a product and I increase it, I got to shift left to consume it. Now let's look at what happens if we increase the pressure. For this first one, there are 2 gas molecules in the reactants, but there are 4 in the product. So if I increase the pressure, I need to shift to the side with less gas molecules, so I'm going to shift left. For B, there is 2 in the reactants and 2 in the products, so changing the volume is not going to change my equilibrium position. For C, we have 2 and 3. So if I decrease the volume, increase the pressure, go to the side with less gas molecules, that's going to be shifting left. And then here we have 1 gas molecule in the reactants and no gas molecule in the products. So if I need to go to the side with less gas molecules, that's going to be in the right. So we can still consider equations that have solids in them, but when counting gas molecules, we only count the gaseous substances. All right, last question. And I like using this question because it's from 1977. How crazy is that? Can you picture these little like hippie 70s disco loving people doing AP Chem? I don't know, just cracks me up. So if you are still listening by this last slide, almost 35 minutes in, you can send me a remind message that says disco is alive. Okay, last example. Delta H is negative. Delta H is negative, so this is exothermic. We have an equilibrium mixture. Predict the effect of each of the following changes on the value of the equilibrium constant and on the number of moles of SO3. Okay, so this is kind of taking this a little step further, because not only are we saying shift right or left, we have to consider where SO3 is, and so what would happen to the amount of it. So if I decrease the volume in this system, decreasing the volume is the same thing as increasing the pressure. So if I have 3 gas molecules in my reactants and I have 2 in my products, if I increase the pressure, I need to go to the side with fewer gas molecules, so I'm going to shift right. So shifting right is going to increase the amount of SO3. And accounting for that is because increased pressure shift to less gas molecules. All right. B, if I add oxygen, adding oxygen is adding a product. So, or I'm sorry. Oxygen is very, very clearly a reactant. All right. So adding a reactant. So if I add a reactant, then I am going to shift right to use up that added reactant, which then again is going to increase the amount of SO3 since SO3 is a product. So my explanation, you got to use up or consume added reactant. All right, last one. If I raise the temperature, so if I increase the temperature, delta H is negative, so it's exothermic. So if it's exothermic, increasing the temperature is like adding a product. So that's actually going to shift this to the left, which is going to then decrease the amount of SO3 since it's a product. And that is because exothermic heat is product, increased temp means adding product for this, since only because it's exothermic. Okay, so looking at it, also asks me what is going to happen to the value of the equilibrium constant. The equilibrium constant is going to stay the same for A and for B. For C, if we raise the temperature, the equilibrium constant in this case is going to decrease because we are shifting left. All right, so thank you guys for listening in this very long lecture. I really apologize for it being so long, but I hope you have a great day, and I'll see you later.